how space, time, and gravity really work. Relativity is the idea that measurements of space and time depend on motion, and that gravity is not just a pull, but an effect of geometry. That sounds abstract, but it cashes out in a plain claim: there is no single universal clock that everyone shares, everywhere, forever. This concept matters because modern life runs on timing. Your phone's navigation, the synchronization behind networks, and the way we interpret black holes all assume we know what now means and how fast signals can travel. Relativity says those answers are not absolute. They are rules for comparing clocks and rulers moving through the world. The central tension is simple to state and hard to swallow. If the speed of light is the same for everyone, then space and time cannot stay rigid. To keep cause and effect consistent, the universe forces different observers to disagree about durations and distances, while still agreeing on what can influence what. By the end of this guide, you'll understand what relativity is, how it works in both its special and general forms, where it's rock solid, where intuition fails, and why it shows up in real technology. The story turns on whether the speed of light can be constant for everyone, without forcing space and time to flex. Key points. Relativity is a framework for comparing measurements made by different observers, not a slogan that everything is subjective. Special relativity explains how time and distance change when observers move at constant high speed relative to each other. The speed of light acts like a universal limit for cause and effect, and that single fact reshapes how time and space must behave. General relativity extends the picture to acceleration and gravity by treating gravity as curvature of spacetime, not a force tugging across emptiness. Time dilation is real and measurable, but at everyday speeds it is tiny. It becomes large only near the speed of light or near very strong gravity. Relativity is already engineered into systems like GPS. Without corrections, navigation would drift quickly. The deepest open problem is not whether relativity works, it does, but how it fits with quantum physics in extreme conditions. What it is: relativity in plain English. Relativity is a set of rules that tells you how to translate measurements between different observers. If you and I move differently, we can still agree on the same physical events, but we may not agree on how long they took or how far apart they were. Relativity tells us how both of us can be right without breaking physics. There are two main parts. Special relativity applies when observers move at constant speed relative to one another. It explains time dilation. Moving clocks run slow compared with stationary ones. Length contraction. Moving objects measure shorter along the direction of motion. And the relativity of simultaneity. Two events that are at the same time for one observer may not be for another. General relativity applies when acceleration and gravity matter. It replaces the idea of gravity as a force with the idea that mass and energy curve spacetime, and that objects move along the straightest possible paths in that curved geometry. What it is not: relativity does not mean truth is relative in the everyday sense. It does not say anything you like can be true. It says the laws of physics are consistent across observers, and that the translation between observers is precise and testable. How it works. Start with the core move of special relativity. If the laws of physics look the same for any observer who is not accelerating, then no such observer should be able to perform an experiment and discover a secret absolute motion. That idea pushes you toward symmetry. The rules must not privilege one steady moving viewpoint over another. Now, add the speed of light. Light is not like a thrown ball where speeds just stack. In relativity, every inertial observer measures the same value for light in a vacuum. If you take that seriously, something has to give, because everyday intuition assumes time as a shared background, and distances are fixed. What gives is the relationship between space and time. Different observers slice reality into space right now, and time passing in different ways. Each observer still describes a coherent world, but their bookkeeping differs. A clean way to hold this in your head is to focus on what remains the same. Relativity doesn't say everything is flexible. It says some quantities are invariant, and the flexibility is the price paid to keep those invariants consistent. One of the most important invariants is the spacetime interval, which plays a role similar to distance in ordinary geometry. Time dilation follows from this logic. If two observers are moving relative to each other, each sees the other's clock ticking more slowly. That sounds like a paradox until you notice that at the same time is not a shared concept across frames. Once simultaneity is handled correctly, The math and the story line up. General relativity builds on a different insight. Locally, being in free fall feels like being weightless. If you are falling and not being pushed by a floor, you cannot tell, in a small enough region, whether gravity has vanished or you are simply moving in a straight line. That idea is the equivalence principle. From there, gravity becomes geometry. Mass and energy distort spacetime. In that distorted geometry, the straightest path is no longer what your intuition expects from a flat grid. Planets orbit because they are following geodesics, the closest thing to straight lines in curved spacetime. This also makes gravitational time dilation unavoidable. If spacetime is warped, clocks at different locations can tick at different rates. Gravity does not just bend trajectories, it reshapes the pacing of time. Numbers that matter. The speed of light in a vacuum is exactly 299,792,458 meters per second. This is not just an astronomer's trivia fact. It is baked into modern measurement because the meter is defined using how far light travels in a specified fraction of a second. If you treat light speed as the conversion rate between time and distance, you get a system where timing becomes the foundation for measuring length. The common misunderstanding is to treat this as about light. It is really about the causal speed limit of the universe. The Lorentz factor, often called gamma, shows how quickly time dilation ramps up as you approach light speed. At 0.5 degrees Celsius, gamma is about 1.155, meaning effects are noticeable but still moderate. At 0.9 degrees Celsius, gamma is about 2.294, meaning moving clocks run a bit less than half as fast relative to the stationary frame. At 0.9 degrees Celsius, gamma jumps to about 7.089. The misunderstanding is assuming the effect grows linearly with speed. It does not. The curve steepens dramatically near C. GPS satellites provide a real-world anchor. The net relativistic effect is about 38 microseconds per day of clock offset relative to clocks on Earth's surface. That sounds tiny, until you translate microseconds into distance at light speed. In 38 microseconds, light travels about 11.4 kilometers. If you tried to run GPS as if time were universal, the system's timing would drift fast enough to ruin navigation. The misunderstanding is thinking micro means irrelevant. In timing systems, microseconds are infrastructure. Mercury's orbit contains another famous number, an extra 43 arcseconds per century of perihelion precession that Newtonian gravity could not account for. General relativity explains that residual precisely as a curvature effect from the sun's mass. The misunderstanding here is scale blindness. 43 arcseconds per century is tiny, but physics is often tested in tiny margins where the math is strict and measurement is sharp. Light bending near the sun is also small but decisive. For light grazing the sun's limb, the relativistic deflection is about 1.75 arcseconds. Again, this is not a dramatic light curves like a river effect in the sky. It is a subtle geometric shift that, once measured reliably, tells you whether gravity is a force in space or a feature of spacetime. Finally, black holes give a compact, memorable scale. The Schwarzschild radius is the radius a mass would need to be compressed within for an event horizon to form in the simplest case. For one solar mass, that radius is about 3 kilometers. For Earth's mass, it is about 9 millimeters. The misunderstanding is thinking black holes are super-dense objects in the everyday sense. The key point is geometric. An event horizon is a boundary in space-time, not a material surface. Where it works and where it breaks. Relativity works extremely well wherever speeds are high, clocks are precise, or gravity is strong. It is essential for satellite navigation, atomic clock systems, and space missions where signal travel time is not negligible. In astrophysics, it is the backbone for modeling black holes, neutron stars, gravitational lensing, and gravitational waves. It also works in the quiet places you do not notice. Every time you treat speed of light as a delay limit for communication across chips, networks, or space links, you are living inside the same framework. Relativity is not optional once you push timing precision far enough. Where does it break? Not in the sense of being disproved in its tested domain, but in the sense of meeting its boundary conditions. The biggest conceptual pressure point is quantum gravity, what happens when you need the quantum rules of matter and the geometric rules of spacetime at the same time, at extreme densities and tiny scales. Another break is more mundane interpretation mistakes. People confuse coordinate-dependent statements, which can change with the chosen reference frame, with physically invariant statements, which do not. In general relativity especially, naive phrases like the speed of light changes in gravity can be technically true in some coordinates and misleading in the underlying physics. Many arguments about relativity are not physics disagreements. They are language disagreements. Analysis. Scientific and engineering reality. Under the hood, relativity is a theory of measurement consistency. It tells you what clocks and rulers will read when you compare them across different motions and gravitational environments. The weirdness is not decorative. It is the minimum structure needed to keep cause and effect stable when there is a universal signal speed limit. For special relativity, the claims hold if you are working in inertial frames or in small regions where acceleration can be ignored. The more you accelerate, the more careful you must be about what at the same time even means for your moving frame, and the more you lean on proper time, the time measured along an object's actual path through spacetime. For general relativity, the claims hold if spacetime is well described as a smooth geometric field. That works spectacularly in most real settings, but near singularities the theory signals its own incompleteness by producing infinities. Engineers rarely touch those extremes, but astrophysicists do. And the mismatch between works beautifully and predicts singularities is a clue that a deeper synthesis exists. A good falsifier would be a clean, repeatable deviation from relativistic predictions in systems where the inputs are understood: precision clock networks, pulsar timing, gravitational waveforms, or lensing patterns. So far, the pattern has been the opposite. As instruments improve, relativity keeps showing up in the decimal places. Economic and market impact. Relativity is already monetized, just not branded that way. Satellite navigation underpins logistics, mapping, finance timestamping, emergency response routing, and a huge slice of consumer convenience. The economic impact is less about relativity products and more about time and position becoming reliable utilities. Practical adoption depends on clocks, calibration, and stable infrastructure. If you build systems that rely on precise timing, you inherit relativistic correction whether you want it or not. The costs show up as complexity, better oscillators, better synchronization, better models of Earth's gravity field, and more careful error budgets. Long-term pathways look like deeper timing precision spreading outward. As optical clocks and time distribution improve, more industries can treat time as a controllable resource, rather than a background assumption. That enables better sensing, better navigation resilience, and new measurement capabilities. Security, privacy, and misuse risks. The realistic misuse risk is not that relativity enables a weapon by itself. The realistic risk is that timing infrastructure becomes a target. If a system depends on nanoseconds, then spoofing, jamming, or degrading timing signals can have outsized effects on positioning and synchronization. Another risk is rhetorical misuse. People overclaim what relativity allows, especially around time travel or faster-than-light messaging. That confusion can pollute public understanding and distract from real engineering constraints. Guardrails here are not moral rules. They are engineering standards, signal authentication, redundancy, multi-source timing, and auditing of timing-dependent decisions in critical infrastructure. Social and cultural impact. Relativity changes how people think about now, but its deeper cultural effect is about humility in measurement. It teaches that even basic categories like time and distance are not detached from the processes used to measure them. In education, relativity is one of the clearest examples of a theory that feels wrong and is still correct. That makes it a training ground for scientific thinking. Follow the logic, test the claims, and accept counterintuitive conclusions when the evidence compels them. If its principles scale into everyday tech more aggressively, the second-order effect is trust. Societies become more dependent on invisible timing systems. The better those systems work, the less visible they become, and the harder it is for non-specialists to notice when they are being degraded. What most coverage misses. Most coverage treats relativity as a set of dramatic consequences. Time slows down, lengths shrink, gravity bends light. Those are true, but they are the surface ripples. The core idea is tighter. Relativity tells you what must change so that some deeper quantities do not. A useful way to say it is, relativity is not primarily about motion. It is about comparisons. It describes what happens when two observers try to agree on a shared reality using signals that travel at a finite speed. The universe is not being poetic. It is enforcing consistency. The second blind spot is that general relativity is often taught with a single analogy, the trampoline, that smuggles in a hidden force, gravity pulling things down into the rubber sheet. The more faithful picture is geometric. Objects follow the straightest paths available. Gravity is not a pull through space. It is the structure of space-time that tells paths how to curve. Why this matters? Relativity matters most to anyone who relies on precise time and position without thinking about it. That includes most people, most companies, and most modern states. In the short term, the impact is practical reliability, navigation accuracy, network synchronization, and the integrity of timing-based services. In the long term, the impact is conceptual and technological. Better clocks and better gravity measurements turn relativity into a tool for sensing and mapping the world, not just describing it. Milestones to watch are less about anniversaries and more about capability shifts. If we see timekeeping move from good enough to physics limited in mass market systems, applications will follow. If we see new gravitational wave observatories, better pulsar timing, or sharper black hole measurements, they will keep tightening the leash on where new physics could hide. Real-world impact. A smartphone navigation fix is basically a time problem. The phone and satellites are solving for location by comparing signal arrival times. Relativity enters because those clocks are not living in the same gravitational and motion environment as yours. A data center is an agreement machine. Distributed systems depend on ordering. Which event happened first, which transaction is final, which log is canonical. Better clocks and better synchronization reduce ambiguity, but they also make timing assumptions more brittle if attacked. Space missions are geometry under pressure. Light speed delay makes remote control impossible at distance, and timekeeping becomes part of navigation, communication, and science measurement in a single bundle. Modern astrophysics is now partly listening. Gravitational waves are direct changes in spacetime geometry arriving at Earth. Relativity is not just an equation there. It is literally what the instrument is detecting. Frequently asked questions. Is relativity just a theory, or is it proven? In science, theory means a tested framework that explains and predicts. Relativity has been tested in many ways, from precision clocks to astronomical measurements, and it keeps matching reality in its domain. The open question is not whether relativity works where it has been tested. The open question is how it meshes with quantum physics in extreme regimes. What is the difference between special relativity and general relativity? Special relativity is about observers moving at constant speed relative to one another and the consequences of a universal light speed limit. It explains time dilation, length contraction, and the relativity of simultaneity. General relativity extends the framework to acceleration and gravity by modeling gravity as curved spacetime. It explains gravitational time dilation, light bending, black holes, and gravitational waves. Does time dilation mean you can travel to the future? In a strict sense, yes, if you move fast enough or spend time in a different gravitational environment. You can experience less proper time than someone else and reunite in their future. In practice, the effect is tiny for ordinary travel. Dramatic time jumps require speeds and energies far beyond current human engineering. Why can't anything go faster than the speed of light? In relativity, the speed of light is not just about light. It is the speed limit for information transfer and cause and effect influence in spacetime. If signals could travel faster than that in ordinary spacetime, you could create causal paradoxes where effects precede causes in some frames. Relativity's structure prevents that. How does GPS use relativity? GPS works by comparing very precise timing signals from satellites. Because satellite clocks and ground clocks experience different motion and gravitational conditions, their tick rates differ slightly. The system includes relativistic corrections so that timing stays consistent and positioning stays accurate. Does gravity slow time or speed it up? Both statements can be true depending on the comparison. In general relativity, clocks deeper in a gravitational well tick more slowly relative to clocks higher up, when compared carefully. That is why a satellite clock can tick faster relative to a clock on Earth's surface, even though the satellite is also moving faster, which creates an opposing time dilation effect. Is gravity really curvature, Or is that just a metaphor? In general relativity, curvature is not a metaphor. It is a mathematical description of space-time geometry, and it produces quantitative predictions about trajectories, clock rates, and light paths. The force picture can still be used as an approximation in many settings, but curvature is the deeper model. Where might relativity fail? Relativity is expected to be incomplete where quantum effects of spacetime itself become important, such as near singularities or at extremely tiny scales. Researchers look for small deviations in precision tests, because that is where new physics would most likely reveal itself first. The road ahead. Relativity's core lesson is not that time is strange. It is that nature is consistent, and our intuitions are local. The deeper you push measurement, the more the universe forces you to trade comforting assumptions for sharper rules. One scenario is that relativity remains exactly right across every new test we can build, and the next layer shows up only as a quantum completion that reduces to relativity cleanly in everyday regimes. If we see gravitational wave and pulsar timing data keep matching predicted waveforms with tighter error bars, it could lead to fewer hiding places for alternative gravity theories. Another scenario is that tiny, systematic deviations appear in strong gravity environments, not in labs. If we see persistent mismatches in black hole ring-down signals or extreme pulsar systems that cannot be explained by modeling error, it could lead to a revised theory of gravity that still looks like relativity in weak fields. A third scenario is that progress comes from timekeeping, not telescopes. If we see optical clock networks become widespread and stable enough to map gravitational potential differences as a routine measurement tool, it could lead to relativity-enabled sensing becoming a practical industry. A final scenario is that the real revolution is conceptual. Gravity turns out to be quantum in a way that changes what spacetime is, not just how it bends. If we see credible tabletop evidence that gravity can mediate quantum entanglement between masses, it could lead to the first direct bridge between Einstein's geometry and quantum mechanics. What to watch next is not a headline. It is precision, better clocks, cleaner signals, stronger gravity laboratories in the sky, and theories that dare to make specific, testable predictions. More insight, less noise. Subscribe and explore the full range at taylortailored.co.uk.